hopefully these should be exciting papers. We'll cover some of these, hopefully next week if we get to it. They'll be on multi-threading. It's an important topic. That's another research area that you can work on, actually, for your projects. How to exploit the multi-threading substrate for something. So if you read these papers, maybe they'll give you some ideas. Then you can certainly read more papers after this. I know one of you have read one of the papers. Okay. Other recommended papers, I probably want to cover related heterogeneity. I guess I randomly picked two of them. So if you're interested, you can look at these two papers. One is on core fusion. When we talked about this briefly last time, you start with small cores and you somehow fuse them to operate as a large core. How does it work? Well, this paper will tell you, except it's a nightmare to implement. So if you actually get to it, if you actually cover it, I'll tell you exactly why it's a nightmare to implement. It's very difficult to get it to work without losing significant performance. And this is one of my students for a childhood paper on stage memory scheduling. It looks into how to do memory scheduling when you have a CPU and a GPU on the same chip, and they share the memory controller. So these could give you some ideas on research also. Okay. The last lecture we covered an early history of multi-core. I gave you the path two big companies have taken, Sun and IBM. One of them is dead, the other is alive, I guess. And they've taken different paths in multi-core. We talked about homogeneous multi-core evolution. I presented within the context of those two companies. And they were trying to achieve something, and I propose that they're trying to achieve the best of multiple worlds, but they're not going to get it without some sort of asymmetry. In fact, they moved to asymmetry also, right? Frequency boosting is one way of achieving asymmetry. We will see, we'll cover that paper that described that first. So today we'll talk more on asymmetric multi-core and maybe talk about asymmetry in general. If you've done the reviews, we'll cover the papers you reviewed. So hopefully you'll have some opinions on some of those papers. But I'd like to go through those relatively fast if we get to them. Okay. Any questions before we start? Everybody's working on their project proposals. I think I talked to many groups, but not all. This is another review. Remember we were talking about two approaches to designing multi-core. By a large approach, you have large cores put together, and by a small approach, you have many small cores put together. And none of them achieve the best of both worlds. So if you have both of them, you can get performance asymmetry, and that enables hopefully best of both worlds. Why? Because you can execute the serial part of the code in the large core and the parallel part on all of the small cores. And if you have multi-threading on the large core, then you can get as good parallel performance as this tiled small approach, and hopefully as good serial performance as this tiled large approach. And remember this was I had introduced EPI throttling. This was one of the first papers that introduced what's called turbo boost now, which is increasing the frequency of a machine when you have only one thread. Right? That's one way of achieving dynamic asymmetry. And the idea is their goal was to minimize execution time of parallel programs when you had a fixed power budget. How can you do this? If you express power as EPI times IPS, EPI means energy per instructions times instructions per second. In phases where you have lots of instructions per second, which means that phases you have lots of parallelism, lots of instructions per second, you can have lots of processors where EPI is low, energy per instruction is low. This is the ideal multi-core in a sense. Whereas in phases where you don't have lots of instructions per second, the serial phases, you can boost the EPI. And one way of doing that is by increasing the frequency significantly. And there are many other ways of doing that. We covered briefly, if you remember, the dark chart. I don't have it right now, but chart talks about different ways of doing that: asymmetric multicore, speculation control, or shutting down some pipeline resources. Okay. And one way of achieving it is using DBFS. Basically, when you have low thread parallelism, run a few cores at high supply voltage at high frequency. When you have high thread parallelism, run many cores at low supply voltage and low frequency. And that's what this paper did. This is ISCA 2005, mitigating Amdahl's law via EPI throttling. And they took a real system and configured it to be statically asymmetric. How can you do this? You can have, let's say, 4 cores. 3 of them are dedicated to parallel phases, and they run at 1.25 gigahertz. And you have 1 core dedicated to sequential phase, and it runs at 2 gigahertz. And you guarantee through affinity settings in the operating system, in the program, that the sequential phase runs on 1 processor and the parallel phase runs on the 3 processors. And they did this on a real system. And they used this approach for benchmarks that rapidly transition between sequential and parallel phases. They also had a version of something like this, but dynamic. They can change the duty cycles during program run through operating system calls. In this case, they enabled parallel phases to run on all or a subset of 4 processors, depending on how many threads you have. And sequential phases were forced to run on a single processor at 2 gigahertz. I think the parallel phases were run on the 4 processors with 1.25 gigahertz. And they use this approach for benchmarks with long sequential and parallel phases. If you have a long parallel phase, then you want to have all of the processors working on your parallel phase. Here, if you're rapidly transitioning between sequential and parallel phases, you might as well dedicate 1 processor for the sequential phase. That's why they did it. I mean, you can question their design choices, of course. So, I guess what did they do? They this was their system at the time. It was a 4-way 2 gigahertz Xeon. So it wasn't even. These were 4 different processors. They were not, as far as I know, they were not multiple processors. There were 4 processors connected via cache coherent substrate. That's a good question. Maybe someone can check that. So they hand modified the programs to enable static and dynamic asymmetric multicore for these different applications. And this is what I already described to you. Make sense? And these are some of the programs that were run on the static configuration. And these were some of the programs that were run on the dynamic configuration. It looks like parallel phases ran on 4 processors with 1 gigahertz in the dynamic configuration. And they could boost the frequency to 2 gigahertz if there was a serial phase. And what did they gain? These are the performance results that are reported in that paper. This is the speed up normalized to 1 processor running at 2 gigahertz. And this is the asymmetric performance of the asymmetric multiprocessor. And this is the performance of the 4 processors that are running at 1 gigahertz. Does that make sense? Comparison points. So this is a single speed up compared to a single core that's running fast. This is the symmetric multicore, and this is the asymmetric multicore. Except it's not a multicore, I think it's a multiprocessor. If you look at these applications, there's significant gain here compared to of asymmetric multicore compared to symmetric multicore. And these applications do not gain that much. It looks like these applications lose regardless of what you do. I think they did not tune the application very well. Does that make sense? So that's the benefit of asymmetric multicore, where you have these applications where you have serial phases. You can boost the frequency and get out of those serial phases quickly, either statically or dynamically. Okay. Yes. They did not see improvements in some applications, even though there were significant serial phases. can read the paper for more detail. I used to assign this paper, but I want to assign you different papers now, more cutting-edge papers. Why would frequency boosting asymmetric multiprocessor not improve performance? We covered this before briefly, right? So even though they had applications where you had some serial phases, they did not see performance benefit.
They have issues with memory latency.
That's right. So some of those phases were actually, well, memory bombs. But this, I'll skip this. You can mitigate that problem. Basically, you're saying this boosting frequency does not help memory bomb phases. So, they also ran into issues when they had rapid transitions between serial and parallel phases. In that case, they needed to, they ran into throttling overhead because they needed to change the frequency and the voltage. And that's in time. So that's one of the, there's an overhead to changing the frequency and voltage, and that's one of the reasons they did not see performance benefits, especially when the serial phase was short, because you cannot advertise the overhead of ramping up frequency and voltage. And in some cases, they lost throughput in the static version of the asymmetric multiprocessor. And hopefully you should be familiar with this because you've read the papers that I've assigned. If you're reducing your parallel performance in the parallel phase, and if you do not have a lot of processors to begin with, then you can lose performance. And in this case, they had only 4 processors, and in the parallel portion of the code, they were running only 3 of them. Which means that whenever they have 4 threads in the baseline system, symmetric multi-core system, they would have only 3 threads in the asymmetric multi-core system in the parallel portion. So there's a 25% loss of throughput in the parallel portion when you're going from symmetric to asymmetric, which is pretty high. You have to overcome that somehow, right, to get the performance improvement. Okay. I'd encourage you to read that paper. That's actually a nicely written paper. I don't think a lot of people recognize that that's one of the first papers that proposed this frequency boosting. I don't think it's given enough credit in the community. It's ISCA 2005. Okay, what did we cover? I think we covered all of this, right? And we covered asymmetric multicore, functional. We didn't cover functional asymmetry, but we briefly covered functional asymmetry. Right? You have CPU plus GPU. That's kind of functional asymmetry, different ISAs. We may get back to that after we cover GPUs. We covered static versus dynamic asymmetry, and API throttling as one example of achieving either static or dynamic asymmetry. Let's take a look at some of the trade-offs in asymmetric multicore. I think you already read this in one of the papers, hopefully, the accelerated critical sections paper. But the trade-offs exist regardless of what you're accelerating on the large form. One big trade-off, as I told you many times in 447, there's a big trade-off between hardware architect's job versus the programmer's job, right? Asymmetry is, in a way, making programmers' life easier, but it's making the hardware architect, the microarchitect's job harder. Why? Because now the microarchitect needs to design asymmetry into the system, multiple cores potentially, and somehow a mechanism to switch between the cores. But now the programmer doesn't need to worry about the serial sections as much, because serial sections are going to be boosted by a very fast core. So that's what I said, I think. Performance of the program becomes less dependent on the length of the serial part, which means that the programmer doesn't need to optimize their code as much. That's what this says. The other trade-off, I hope this is clear. I'm going to go through this relatively quickly. The other trade-off is you have migration overhead or some sort of overhead to switch between, switch to the fast mode, if you will. If you're doing a frequency boosting, dynamic frequency boosting, you need to ramp up the voltage and frequency. It takes some time to do this. If you have a large core and you migrate the serial section, that part. You need to either migrate the data or the code, and it takes time to do that. That's the overhead that comes with an asymmetric design. But the benefit is you're accelerating some sort of bottleneck, right? It could be the serial bottleneck in this case, and in your paper, in the papers you reviewed, it was the critical sections, or the barriers, or slow pipeline stages. Oh. I'll cover these without asking you for now. So the benefit is you get performance gain from here, but then you get performance loss from here. And the performance loss comes from multiple things, right? You may need to switch the architectural state to the large core, depending on whether or not that large core already had the architectural state. In the papers you reviewed, the large core already had that architectural state, so that will not be a problem. If you're executing the serial portion of the large core, it incurs cache misses when it needs data generated by the parallel portion. All of the parallel clusters, the parallel portion is running on other clusters, and when the serial portion starts on the large core, it needs to gather that data if it needs it. Similarly, the parallel portion incurs cache misses when it needs data by the generated by the serial portion. And hopefully you've seen some papers that try to marshal the data earlier. This one last trade-off is, and this is not necessarily true because you can have multi-threading in the large core. In the asymmetric case, you have fewer threads if you dedicate the large core to only serial sections or critical sections. Right? In the parallel portion, then you have only you have fewer number of threads. The trade-off is you're accelerating the serial bottleneck. So you get performance gain because of acceleration, but performance loss due to the unavailability of some number of threads. Make sense? Of course, this need not be the case. You can have the large core, you can implement multi-threading in the large core, such that all of your hardware resources are available for the maximum number of threads you would have, as in the symmetric case. And even if you do not do that, as the number of cores on chip or threads on chip increases, the downside of this fewer threads, downside of dedicating a large core to a particular task decreases, because the fractional loss of throughput in the parallel portion decreases. Does that make sense? For example, in the 4-core case, they were dedicating one core to the serial section. The fractional loss of throughput in parallel portion is 25% in that case, right? Whereas if you had 64 cores and dedicate only one core for the serial section, then your fractional loss of throughput is only 1 divided by 64. Okay? Okay. So we'll cover a bunch of other uses of asymmetry. And I would encourage you to think of other uses. This will be more of a researchy lecture. Because going forward into the future, as I will tell you in a few slides, asymmetry is a very good way of enabling very high efficiency as well as very high performance at the same time. So far, you covered improving serial performance, at least in lectures. You read papers that do other things. And this already exists in existing clusters, right? So you can do frequency boosting. We already have dynamic asymmetry. But what else can we do with asymmetry? Any thoughts? Save power. Improve energy efficiency. That's right. You could reduce energy, or you could achieve a better energy performance trade-off. And you already read the paper, so that answer wouldn't count at this point, perhaps. You can improve the parallel portion also, and we'll get to that. Anything else? Yes?
Improve functionality on chip, like the GPU on chip versus having it as a separate off-chip communication.
That's right. Yeah, you could do that. That's more of a benefit of integration, though, when you say you move functionality. You're moving some asymmetric functionality that used to exist outside the chip onto the chip. And that's in the end enables many things, which is reducing costs, potentially saving system power, overall system power. What else? Anything else you can enable? Maybe you guys can think of it. So, actually, one of the first papers that talked about improving energy efficiency with asymmetry is this one. It's called Serialized Heterogeneous Multicore Architectures. The idea was very simple. You could put multiple types of cores on the chip and monitor the characteristics of running threads at any given time. One way of doing that, you could potentially sample the energy per performance you're getting on each thread, and dynamically pick the core that provides the best energy performance trade-off for a given phase. That was the idea. I'd encourage you to read the paper. And best core, of course, depends on the optimization metric, but I'll give you an example with pictures from the paper, I guess. So what they did was they took all the alpha processors, the EV series. This is the EV4, EV5, EV6, and EV8, which never saw the day of light. Or you can think of this alpha 21264, 21464, and 21164, and 21064. And they scaled, and these are cores from different technology generations, right? And they scaled the size of this to, I guess, 0.10 micrometers. Is that 100 nanometers? I guess that's 100 nanometers. And it turns out when you scale the size of these cores to the same technology generation, EV8, which is a very heavily multi-threaded auto-order engine, turns out to be 80 times the size of this EV4 core in terms of area. It's interesting, I think. And if you look at the performance, according to what they say in the paper, it provides 2 to 3 times higher single-thread performance. So that square root law doesn't work, I guess, right? At least for this. The square root of 80 is 9, not 2 or 3. Because technically it's not 9, it's only plus than 9. I'm rounding up. Okay? And they did some calculations. This is, if you look at this table, you can read this table from that far. This tells you the peak power, average power, and performance of these 4 different cores on single thread. So peak power of EV4, which is a single issue in-order engine, is 5 watts. And EV8 is about 93 watts. And performance is 1 normalized versus 2.14. Now you have an energy performance trade-off, right? And if you look at the peak power in the middle, you get, or average power, you get a trade-off. So what they did was I think this is a profile of the same thread if it's executed on different cores. This is the committed instructions, and y-axis is the instructions per second. How many instructions per second is retired from this thread. And if you look at this, there are some phases of this thread where it doesn't matter that much which core the thread is executing on. Instructions per second is relatively similar. Whereas there are some other phases where IPS is very different between different cores. For example, here, EV8 provides much higher IPS here compared to EV4. So if you can somehow monitor some metric, you can switch between the different cores to get a good energy performance trade-off, depending on what you're optimizing for. You could be optimizing for, I guess, performance per watt, right? You could monitor the instructions per second on different cores, and you could decide to switch to the core that provides you the best performance per watt. question is, how do you do that? You're running, let's say the thread is running on one core. How do you know what performance per watt you're going to get on the other core? Any ideas? No ideas? Nobody has any guesses? Well, one thing you could do is you could sample, right? You could run the thread on all the cores and see what performance per watt you're getting. Because you can monitor performance and you can monitor power. And then decide, oh, this core gave me the best performance per watt in this phase, so I'm going to switch to that core in the next phase. That could be one algorithm. May not be the best one because now you're losing a lot of throughput. That's what they did. I think in this paper it doesn't have a very realistic algorithm. That's the downside of the paper. I think it's kind of magically discovers which core is good. But assuming that you could do that, this is the core. This is the best core you select. If you're optimizing for energy only, so you're not always executing on EV4. You're actually executing most of the time on EV6 if you're optimizing for total energy, according to these results. If you're optimizing for energy delay, this is what they found. I encourage you to read the paper. But does this make sense? So this is one way of visualizing multiple different types of cores to optimize for energy or energy delay. There are open research questions here. How do you figure out what your performance would be on a different core while you're running on this core? For example, if you had the ability to switch a program seamlessly from a CPU to a GPU, how do you decide to do that? Assume that you could seamlessly execute the same program on the CPU and the GPU. And I strongly believe that this will happen in the future. How do you decide whether you should execute this program on the CPU versus GPU while the program is executing only on one of them? So you somehow need to have a model of what performance or what power you would have gotten if you were executing on this other type of core. If you can build a model like that, that would be very valuable for many things. You could do the scheduling in hardware, you could do the scheduling in the operating system. Provide this model to programmers such that they understand what happens, although you may not want to do that for all programmers. But that's an interesting research direction, certainly. Not necessarily only for CPU versus GPU, but also this type of cores as well. Okay. So I guess what are the advantages of using asymmetry to improve energy efficiency? I'll give you some of them. You get more flexibility in your energy performance trade-off. Now you enable, look at this, if you look at this range of energy and range of performance, it's a big range. You can consume 5 watts versus 95 watts, almost. And you can get 1x performance versus 2x performance. And you can probably design better cores that get more than 2x performance. And if you can do so, you can execute the computation on the core that is best suited for that computation. Ideally, if you can identify, if you can dynamically generate the core that is best suited for the computation you have, maybe that's the best you can do in terms of energy efficiency. Maybe that's the limit of your energy efficiency. It's not clear how you would do that, but it's a good, worthy goal to strive for. Of course, there are disadvantages. I think some of these disadvantages we already covered. Well, we did not cover this one. What if you decide the core incorrectly? Then, of course, you may lose efficiency. Because you may be executing on a heavy core when you're not benefiting from that heavy core, large core. There is always the overhead of switching between the cores. You may need to migrate data, instructions. And all kinds of disadvantages of asymmetric multi-core are still there. And you need algorithms to somehow monitor these phases and match the best core to that phase. And there are lots of questions related to that. I think I'll cover this in a little bit more detail in a few slides. This is the paper actually you read, right? So we covered using asymmetry for energy efficiency, but you can use asymmetry to improve parallel portion performance as well. And you read the papers. If you shift the critical section to a large core, you can improve performance in the parallel section. So I'll not cover this right now. Instead, I'll switch gears and talk about asymmetry everywhere. So why can't we extend this notion? So far we've been talking about cores only, right? But there's nothing fundamental about just a core. Why can't we have asymmetry everywhere in the system? You can have asymmetric caches. You can have asymmetric interconnects. You can have asymmetric memory controllers. You can have asymmetric memories. Does that sound reasonable? No? Some of you are smiling. I would argue that it's actually, maybe that's how you can optimize for energy and performance at the same time in the best way. Well, let me give you some of the slides that I have actually covered in one of the NSF, National Science Foundation workshops on what direction should computer architecture or computer design take into the future. Well, this will be high level and somewhat speculative, but hopefully that'll give you an idea of what direction computer architectures may be taking going into the future. So if you look at the design of systems today, what we're increasingly having on chip, off chip, in a cluster, even across the world, are hardware resources that are shared among many different applications. Like when you execute something, when you go to a website, do you know where that code is executing? It's going to be executing in Google's data center and, I don't know, wherever they have data centers. Okay. So you have this big hardware resource that exists everywhere, and chip is a small scale version of it, that is shared among many threads and applications. And I call it the many-core system here to the moment. And then, what are these resources? If you look at a single system, cores, caches, interconnects, memory, disks, power, lifetime, all of these can be considered resources that are shared by many things, many applications. And management of these resources is a very difficult task. Think about who decides where your code executes. When you submit a job to a cluster, somebody needs to decide where that executes. And why is this very difficult? If you look at a multi-core system, let's constrain ourselves again. When you're designing a parallel program or multi-program workload, if you want to optimize the performance, these resources are shared, and it becomes difficult to optimize performance because threads interact unpredictably in these resources. You know this very well from your previous courses. When you have a memory scheduler that's unfair, one thread can be denied service for a while. Now, how do you schedule computation on these shared resources when you do not know how the threads will behave? And arguably, power and energy consumption is the most valuable shared resource because you cannot increase that. You're limited by how much power you can supply to a chip, or a data center, or a cell phone. And this is the main limiter to energy efficiency and performance. So a lot of the things that I said before is true, which is the programmer is a very valuable resource also. That's a different kind of resource. And programmer already has a hard time writing sequential software. How many of you guys have written simple programs and without any bugs at all? Anybody? I'm going to give you a prize if you actually had no bugs in your code so far. Did I hear someone? Okay. How many of you have written parallel programs without worrying about shared resources and didn't have any bugs? Have you written any parallel programs? Yeah, you have probably. Well, hopefully. And even if you don't need to worry about where do these threads execute, it's very difficult to write these parallel programs. But now let's say you want to optimize the performance of multiple threads. You're writing a program that has 100 threads. And you want to optimize its performance. And to be able to do that, and these threads are executing on these shared resources, let's say memory that's shared between many threads. And you have no idea which thread is getting prioritized over the other one. How would you optimize that program? I guess the right answer is I don't know. Could be. So it's very difficult to even write the program, even write a sequential program. If you expose these shared resources, caches, memory scheduler, or even multiple threads on the same core to the programmer, it'll be a nightmare for the programmers. So programmers should not worry about hardware resource management. And there are cases where programmers actually worry about hardware resource management. If you look at a lot of supercomputers, programmers worried about the hardware resource management. If you look at GPUs today, programmers still worry about hardware resource management. Right? You need to figure out how to lay out your data such that it maps to different banks so that you do not get conflicts between different threads when they access your data. And I would argue that that's a nightmare. It is a nightmare if you're programming GPUs, I think. I don't know, is it a nightmare? Yes, it is. So the programmer should not be worrying about this, worrying about what should be executed where with what resources. Where should the data get mapped? That should not be a programmer's job going into the future. So future computer architecture should be designed to minimize programmer effort, to optimize parallel programs. But somebody needs to do this management, right? You cannot avoid it. Somebody needs to map the data to these banks, memory banks in a GPU memory system. And that should be done automatically. And that should be the runtime system that hopefully some smart programmers design. Or maybe some library-based runtime system that gives you a virtualization layer. If you'd like to think of it that way. The programmer writes programs. In between the hardware and the program, you have this runtime system, or hypervisor, someone might call it. You could think of all of that being the same. That maps the programs and the data to the underlying resource. And that resource could be, again, anything, right? It could be, you could think of having your program written, and while it's running on your cell phone, this runtime system decides to ship part of your program to somewhere in the cloud, in some data center. You have hardware resource on your cell phone, you have resource on the cloud. How do you decide? How does the runtime system decide where it takes you? Okay. So, if the programmer is not managing these shared resources, the system should manage power and performance automatically across these applications. And I think there are three major goals. One is we'd like to minimize energy and power consumption, for sure, while satisfying performance requirements. And we will talk about this later on, but you've seen it in earlier courses. And we would, of course, like to minimize program errors. And this, if you look at everything from this context, there's no question that you have to have asymmetry or configurability in your resources. Because if you do not have that, you have no choice. If everything is symmetric, like this, then you have no choice in terms of energy or performance. If your program requires more than this resource, you're not going to get high performance. Well, you can say that programmers should parallelize the program, but that goes against the programmer effort argument. if your computation requires less than this resource, and specifically I'm not calling it a core because it could be any resource, then you'll be suboptimal because you've given it more than it needs. So asymmetric, if you look at an asymmetric system, it enables us trade-offs and customization, and that's the main benefit of an asymmetric system, that enabling of the trade-off. Because processing requirements vary across applications and phases, you can execute the code on the best fit resources. If you need more, you execute the code on this big C1. If you need less, you execute the code on the small C5. That's the benefit of asymmetry. So if you take this, I'll remain within the chip for now, I guess, but if you take this to the limit, if you will, you can design each hardware resource with asymmetric components. If you look at the cores, you can have big, high power, high performance cores, some medium cores, even smaller cores, and many, many small cores. You could design the caches in different ways such that they're optimized for different access patterns. Maybe you don't have caches for some access patterns. Like you have stream buffers, which we've talked about in the previous courses. Or maybe for different access patterns, you have different memory hierarchies. Basically, each resource, main memory including, can have asymmetry that enables different power, performance, maybe reliability characteristics. And this can fit different computation, access, and communication patterns. And you can design a runtime system, cooperatively, hardware and software, to automatically choose the best fit components for each phase. The runtime system has the smarts, if you will, to stitch together the best fit chip. It has this pool of resources, and it says, I'm going to take this medium core from here, and this hierarchy from here, and this interconnect from here, and this main memory from here, and allocate it to this particular computation phase that I have at hand, that I know a lot about, based on some past information or based on something that's given to me. That way, maybe among this pool of resources, you can carve out a best fit chip for that phase. And if you have this, maybe there's another opportunity. You can have software that's written or translated to execute on multiple components. And the runtime system can choose between the software components also to be able to achieve this task. You know, your task may be, what could it be? What do you do mostly? Playing Angry Birds. To play Angry Birds, you can have different software. And it could be fit for executing on different resources. If you're running very low on your battery, for example, maybe your Angry Bird will execute on the cloud, and there will be another software. It could be written in a different, probably usually it is different, written in a different code base to execute on the cloud versus to execute on your cell phone. So you can morph the software components to match different hardware components, but you could imagine doing this on the same chip as well. So you can have multiple versions for different resource characteristics, and depending on the availability of some of these resources, you can execute the code, execute different code to accomplish the same task on these resources. So that's the idea of asymmetry everywhere. This is a summary of it. So how do we get there? It's of course not easy. There are many research and design questions that I'll leave you with. How do you design these asymmetric components? What monitoring do you perform cooperatively in hardware and software to achieve this? How do you characterize a phase? You could do this at different granularities also, right? You could do it at granularities of tens of instructions. Or you could do it at granularities of much larger software components. That's another question. What's the granularity at which you decide what resources you allocate to a particular computation? How do you design the feedback control loop between the hardware components and the system software? And how do you design the runtime to automatically manage these resources? These are very big research challenges. give you some small baby steps, or maybe you've already seen some of the baby steps in the papers. Okay, this is the summary. I'll just move on. So how do we get there? I don't know if we'll be able to cover all of this in this lecture, but I'll give you some examples first, and then we'll cover quickly some of the things you read. And we'll also go into asymmetry in memory, and we'll continue on asymmetry in memory on Friday. Okay, some examples. You've already seen these examples, right? You can execute the serial sections or critical sections on high power, high performance cores, and non-critical sections or non-bottlenecks on low power, low performance cores. What is the benefit? Now the programmer can write less optimized but more likely correct programs. And you can improve both power and energy efficiency. And the papers you read, the bottleneck identification and scheduling, accelerated critical sections, it shows that you can improve performance. But it turns out that improves energy efficiency also. What else can you do? You can have different memory hierarchies, some optimized for streaming, and some optimized for random access. And depending on what accesses you're making to different pieces of data, you can allocate the data into different hierarchies. That way you can get higher efficiency and higher performance than a general purpose hierarchy. Because if you're doing random access, and if you have caches, if you have a very multi-level cache hierarchy, L1, L2, L3, L4 caches, then you move that data that you're never going to reuse into all of your caches, and then move it back after you write to it. So what's the point of doing that, right? Why not, for example, maybe when you're doing random access, maybe you should be doing that random access very close to memory. Maybe you move the computation closer to memory, and that could be a hierarchy that's optimized for random access. Or maybe you have a streaming buffer. Even if you're streaming, just purely streaming without any reuse, caches are not very effective. You just need a small streaming buffer where you stream the data and use it, maybe write to it, and then push it back to memory. You don't need this big bulky cache hierarchy that's really optimized for reuse, right? If you don't have reuse, either temporal or spatial, then your caches are not very useful. In fact, they're very inefficient. They add latency and they add power consumption because you're keeping this data that's not being used. Yeah. And that could be another interesting topic, by the way, another research topic that to do in this class if you're still looking for research topics. We have talked about this in previous classes, and we will probably get to it again, especially for the on-chip network part. You can have different kinds of or partitionable memory controllers, partitionable interconnect. And based on the thread's different needs, you can partition the bandwidth asymmetrically. Because some threads need more, some threads need less. Or you can have different kinds of memory scheduling policies, for example, for different types of threads. And dynamically, you can choose the memory scheduling policy depending on what thread is executed. Fusion. I guess we haven't covered all of this in 447. So some threads could be bandwidth sensitive, some threads could be latency sensitive. If you can dynamically distinguish between those threads, you may want to employ different policies for those threads. For the latency sensitive threads, you really would like to prioritize them over other threads because they need the quick data from main memory. For bandwidth sensitive threads, you really want, if you have many bandwidth sensitive threads, you want all of them to make some progress, get their bandwidth. And we will talk about some scheduling policies where bandwidth sensitive threads, the memory controller round robins among the bandwidth sensitive threads such that each thread gets its chance to get the bandwidth it needs. So you can have different scheduling policies. Or you can have a main memory at this level with different technology characteristics. We will go into this in more detail on Friday. But the idea is maybe you don't want all DRAM in main memory because it may be very costly. may be very inefficient, right? It requires refresh. But if you have some other technology that has better energy characteristics, for example, phase change memory, or some other memory technology, magnetic memory, that doesn't require refresh. Now you have a choice again. It could be non-volatile. It doesn't require refresh. Now you have multiple memory technologies, and you can place the data that's latency critical to DRAM, but other data that's not latency critical to some other memory technology that's relatively slow but doesn't consume as much energy. We can map pages and applications to the best memory resource. So we can build the entire system this way. And wouldn't the world be much more efficient if you could do this? Okay. Should we take a break or should I keep going? It's a good point for a break. Maybe we should take a 5-minute break and then we can continue with some more concrete examples. I'll probably go through this relatively fast since you read it. So I'd like to hear your questions about it if you have them. Let's take a 5-minute break. On these 3 papers. So we're going to accelerate the parallel part, or bottlenecks if you will. And this is also a very important research problem. So if you're going to look into this, let me know. If you look at a parallel application, there are many serialized code sections. Programs are split into threads in parallel applications, and threads execute concurrently on multiple cores. The problem is many programs cannot be parallelized completely. That's what Amdahl was worried about. And we've seen the curves in the last lecture in terms of how much performance you would get with asymmetric multi-core. And if you remember the curves, even if you have parallelization, 99.9% of your program parallelized, still you need a beefy core. The serialized code sections reduce performance, limit scalability, and waste energy. And you've seen this in the papers you read. So what are the causes of these serialized code sections? There are 4 of them here, but you can come up with more. And I'd encourage you to think of more reasons why you have serialized code sections. Sequential portions are the obvious one. That's what Amdahl talked about almost 50 years ago. Critical sections, barriers, and limiter states in pipeline programs are others. So hopefully you know all of these because you read the bottleneck identification and scheduling paper. But this is a summary of it. What's a serialized code section? It's any code segment for which threads contend. So one thread makes another thread wait. And serial portion, you know that. Critical sections, these ensure mutual exclusion. If two threads cannot update, or when one thread is updating some data, some shared data, another thread cannot read it because you may get inconsistent state. That's the purpose of a critical section, to ensure mutual exclusion. And if a critical section is contended, one of the threads, at least one of the threads needs to wait, because only one thread can be in the critical section. And this could become on the critical path of execution of a multi-threaded program. If you have barriers, barriers ensure that all threads reach a point before a thread continues, right? Before any thread continues. And you can have barriers between subsets of threads also. And this means that the latest thread that's arriving at the barrier, if it's slow, is on the critical path because it's making everybody else wait. So that's another bottleneck. And this happens because of many reasons. It could be because your load is imbalanced across the thread. Some thread has more work to do. It could be because some thread gets more cache misses than the other thread. That's why it's getting to its barrier late, even if the load is perfectly balanced. It could be because, again, some thread gets delayed in some resource because some other application is accessing that resource, whereas all of the other threads do not get delayed, right? As a result, one thread will be arriving latest. And there could be many, many reasons, especially when you're sharing resources between multiple applications. pipeline stages. You guys know about pipeline parallel programs? Have you written any of those? No? If you know about them? You read this paper, right? About like identification and scheduling. But you can, one way of parallelizing programs is writing them in a pipeline parallel fashion. Which is, you can think of it this way. Let's say you have a loop, for loop or while loop, it doesn't matter, and some code, A, B, C. And this A, B, and C communicate little with each other. There's some communication, but not a whole lot. And you have these different loop iterations. What you can do is you can parallelize A, B, and C from different loop iterations. So you can actually do this. You can have processor 1, processor 2, processor 3. Processor 1 is dedicated for executing A's, processor 2 executing B's, processor 3 executing C's. It doesn't need to be dedicated. And you have loop iteration A0, A1, A2 here, B0, B1, B2, dot, 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 executed here, C0, C1, C2, dot, 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 executed here. This is one way of parallelizing a loop iteration. Yes?
One thing I didn't really understand reading the paper on this is that saying that there's no inter-iteration dependency. Like if you have a for loop that's summing to some accumulator register, right?
That's right, yeah, that will be difficult to parallelize potentially.
And is it generally true that I guess in most code you don't have that kind of dependency? It seems like that might occur fairly frequently.
Yeah, if you have a cross-iteration dependency, that's difficult to parallelize.
And that's not so common that this is just, I mean, so it's rare enough that this is still useful.
Yeah, this is still used in many programs. It's not, I wouldn't say it's rare enough. There are many programs where you have inter-iteration dependencies. But that's, and we will cover how to parallelize some of those. Yeah. But that's the tough part of parallel programming, right? If you have inter-iteration dependencies, how do you parallelize those? So in this case, one reason to do this kind of parallelization is these A's may be working on some data set that you want to keep local in processor 1. And these B's may be working on some data set that you want to keep local here. And these C's could be working on some data set you want to keep local there. That way you can get better locality as well. So that's the idea. This is one way of doing pipeline parallelism. Make sense? So in this case, if you have this, basically different stages are executing on different threads and potentially on different cores. Now the slowest stage makes other stages wait. And there are other issues if you have many of these, load imbalance issues, for example. But that slowest stage becomes on the critical path. Let's take a look at critical sections first. You know what those are, so I'm going to skip that. I'm going to skip this also. But this is a real example from a real database system, but you can, it's high level, so you can actually look at the code. Let's say you have, I'll give you a cooked up example, but a real micro benchmark-like example, where you have 12 loop iterations, and 33% of the instructions of the loop iteration are in the critical section. So if you execute this on a single processor, this is what the execution time would look like. There's some critical section that the processor is executing, and it's 33% of the time. So you'd execute it in 12 time units. Of course, critical section doesn't matter in this case, right? Because there are no, they're in multiple threads. If you execute this on two processors, this is what the execution time would look like. You get benefit from parallelization. And when one thread is executing critical section, the other thread cannot execute. So there's some serialization. If you execute this on 3 threads or 3 processors, this is the performance you get. You still gain performance. Now if you add one more thread, you can no longer improve performance. Because now what happened is, here the program is critical section bound for you. At any given time, one of the 3 threads is executing the critical section. And if you parallelize the program more, add one more thread, you don't gain performance. In fact, if you run this on a real system, you will lose performance. Why? That's right, yes. Because if you add one more thread, you're not gaining performance, obviously, because your performance is bound by the critical section. But now, one more thread is locking and unlocking and accessing shared data, which means you're moving more data. Well, you're doing, you have one more processor where the data is moved to. And there's overhead of locking and unlocking operations too. So you would normally lose performance going from 3 to 4. There's another reason, which is the resource contention. You could actually be contending for the cache and main memory more when you have more threads. So if you magically accelerate the critical section by twice, this is what you would get. In a single processor, you would get some performance improvements. With 2 threads, you would get some more. With 3 threads, again, you would improve performance. And with 4 threads, you would improve performance also. But if you look at this, now, the program scales from going from 3 to 4 threads. The performance actually improves going from 3 to 4 threads if you accelerate the critical sections. Because you're no more critical section bound here in terms of your execution time. So that's the insight. Accelerated critical sections increase the performance and scalability. And how do you achieve that? You already know the answer. I guess I'll give you an example from a real application, MySQL. This is as you increase the number of threads in terms of chip area. This is the performance you would get. This is a very common speed-up curve. It's called parallel speed-up curve. Speed-up of this is with a single thread, your speed-up is 1. Basically, speed-up is normalized with a single thread. And as you add more threads, you get better performance up to this point. At 16 or so threads, you get almost 6x performance. Your speed-up is 6. But if you keep adding more, your performance starts reducing in this database workload. Whereas if you accelerate the critical sections, you could get a curve like this. And you know how to do this now, right? Okay, I will not cover this in more detail. Basically, how do you accelerate critical sections? You can shift them to the large core. And I will let you go through this. Right? Has everybody read the paper? Yes? Maybe some of you didn't? I'll give you the basic idea. Some of you are sitting in class, so maybe I'll go through that. So in a conventional system, when you get a critical section, you basically need to transfer the lock from one processor to the other processor. Whereas if you accelerate the critical section, you need some sort of scheduling buffer in the large core to keep track of the critical sections. And how does that work? This is called this critical section request buffer. When P2 encounters a critical section, that critical section is marked with a special instruction, critical section call. This P2 sends this critical section request to the critical section request buffer, and P1, which is the large core, executes the critical section. And hopefully it executes much faster than P2 would have executed. And when P1 is done, it sends this critical section done signal to P2, so that P2 can now continue executing. Of course, this requires support from many different parts of the system. ISA needs to change such that you have a critical section call instruction and a critical section return instruction. And somebody needs to insert these critical section call and return instructions. Compiler and library is a good place to do that. Such that the programmer doesn't need to do that. The programmer certainly could do that, but if you require the programmer to do that, it may not be a good idea. And I already told you what happens. Actually, I'll give you this example. Basically, the code needs to get transformed from this version with lock and unlock. This is the critical section. and this is what the small core would execute normally. Before doing the critical section call to the large core at the target PC, which is the beginning of the critical section, the arguments into the critical section needs to be pushed on the stack. So how does the critical section communicate with the non-critical section? Through the stack. It doesn't need to be that way, but this simplifies some things. That way critical section calls can be outlined. They could be functions. And a lot of library-based programming models have critical sections as functions. If you program with OpenMP, you have critical section function calls. And when this critical section call gets executed, it gets translated into a critical section call request that gets sent through the interconnect to the large core. So what gets sent? The log address, the target PC, the stack pointer, and the core ID that requests the critical section execution. And in large core, it gets queued in this critical section request buffer, and at some point it becomes the head of that queue, which means the oldest critical section that was sent. And the large core takes the critical section and starts executing from the target program counter. And the code at target program counter first acquires a lock, and then pops the input to the critical section, which was pushed by the small core. And you know there's a name for this, right? That's a thread private data that gets input into the critical section. Or inter-segment data, if you remember from the data marshalling. These are all familiar, right? Okay. And that thread private data is used in this critical section call here. And at the end, the large core pushes the result onto the stack, releases the lock, and returns from the critical section. And this critical section return generates a critical section done response, which is sent to the core ID associated with the critical section request. And when the small core gets the critical section done response, it pops the result that was produced by the large core, and I guess does whatever it needs to do. Yes?
You mentioned that if the small core were to get interrupts while the large core is executing the critical section, that it would wait for the large core to return and then service the interrupt.
That's right.
What happens if the critical section is really long and the interrupt is like time critical?
Yeah, you need better support than what the paper suggests in that case. That's right.
So could it like tell the large core to abort if the interrupt were?
Yeah, you could certainly do something like that. If the interrupt is for that small core, maybe you have another mechanism that says abort the critical section. Of course, that complicates the system a little bit. I think a better solution perhaps is to have the interrupt redirected to some other core.
So
You don't have to execute that interrupt in that core.
So it can like send the interrupt handler to the large core?
Or somewhere else, some other core.
Oh.
Some other core that's not waiting for this request. But that's a good question. There are system level issues that you need to handle. If you would like to design a system that where the critical section waits. At some point, actually, in the multi-threading lectures, we will see that if you have a separate thread context in the small core, that thread context can handle the interrupt. We'll cover a paper called the use of multi-threading for exception handling. And that's one of the benefits of multi-threading. If you get an interrupt in this core, and you keep one thread context active just to handle interrupts or do system level functions. And that way you can handle the interrupts much better. But I think a better system level solution is actually to redirect the interrupts to particular cores that do not do this kind of waiting. So basically you're specializing the core for interrupt handling. That's another case for asymmetry, if you will. That makes interrupt handling easier. And also potentially better because you have better locality in the interrupt service routines, depending on what interrupts you're handling. But interrupts are external to what's running, right? not that program, but the interrupt can come from anywhere, right? It could be a device that's interrupting the world. If it's a time critical interrupt, it may need to get serviced, right? If it's a machine check interrupt, for example.
That's why the good practice is
That's right, yeah. I mean but then now you're putting the burden on the program. Yeah. So the system needs to handle that regardless of the length of the critical section. Yes?
Large code is handling different data section requests in first order. Wouldn't it make sense to prioritize something on which more number of cores are waiting? For
That's right.
example, if there are 3 cores waiting, 3 small cores waiting on something which should be pushed forward to be.
So have you read the bottleneck identification scheduling paper? That's what that paper does. So this is the original idea, but that's a good idea. If you know which, actually that's not exactly what the paper does. If you know which critical section causes a lot more waiting, then you prioritize that critical section over the others. And this is still an open research area. That may not be the best option, right? Because that critical section that you prioritize may not benefit from executing on the large core. None of those papers you've read take that into account, right? The assumption is that hopefully if you ship a critical section to the large core, it executes faster. But that may not be true. But that's simple to do. Otherwise, how would you figure out whether a critical section would execute faster? And that's the next step in research. Okay, those are good questions. If you're interested in that interrupt handling question, maybe you could do your project on that. There are a lot of interesting issues actually related to that, and when you have multiple applications also put together, not only the one application executing on the cores, but another application that has critical sections executing concurrently. Which one do you prioritize? That's another interesting issue. Okay. Yeah, you already figured out the false serialization, hopefully, after reading the papers. One issue with this kind of system is you can serialize independent critical sections because you're shipping all of the critical sections into this large core and scheduling them in FIFO order. Now, if you have 2 different critical sections that are independent of each other, critical section called A, another critical section called A, these need to be serialized. Of course, we'll cover some work that actually parallelizes these also later on. But to maintain the semantics of the lock, mutual exclusion, these need to be serialized, so that's fine. But if you get a critical section call request from some other core to block B, this doesn't need to wait for block A or critical section A to execute, right? But in this system, it does wait. So, as you remember from the paper, hopefully, there are saturating counters that keep track of how often does this serialization happen. And if it happens too often for a given critical section call, that critical section call stays in the small core. It's a reactive mechanism. You can imagine better mechanisms. But then the downside could be maybe this critical section is more important, right? Maybe it's better to execute that. So hopefully we'll do better with the bottleneck identification and scheduling. Okay, so what are the pluses? You get faster critical section execution. There's another benefit of executing critical sections on the same place. It doesn't need to be a large core. It just needs to be same place. And that's shared locks stay in one place, right? You get better lock locality. The lock doesn't ping pong between different caches. And shared data also stays in hopefully large caches. You get better shared data locality. Shared data doesn't ping pong. Because the critical sections, the code that accesses the shared data always executes on the same form. Minuses, if you actually dedicate the large core for critical sections, you get reduced parallel throughput. If you do not dedicate it, now you lose locality. Or if you have multi-threading to partially dedicate it, you may lose from the benefit of acceleration. Right? while you're executing executing a critical section. If you're executing something else also, then you lose the benefit of, some of the benefit of acceleration, because you don't have the full resources of the large core to execute the critical section. Another minus is the transfer overhead, right? It says locks stay in one place, you get better lock locality, but locks are kind of transformed into this critical section call and critical section dump signals. And there's some overhead to that. The good news is that if the critical section is actually contended, that overhead is not on the critical path. Because while you're sending this critical section call to the large core, another instance of the critical section is executing on the large core. So you're overlapping that latency of execution with the transfer overhead. So it makes sense to do this for contended critical sections. Whereas if a critical section is not contended, this overhead becomes on the critical path, right? Because you're sending a critical section that's not contended to the large core. You're just delaying this thread. And you've already read a paper about this thread private data. This data that we pushed, right, A, that we pushed on the stack needs to be transferred to the large core. Which means that you get worse private data locality. The data that's needed by the critical section, you get worse locality. This was not a problem if you were executing critical sections on the same core. But hopefully, as you read the data marshalling paper, you see that it's an easier problem to solve. Why is it an easier problem to solve? Because you can identify the data that needs to be transferred to the critical section, to the large core early, and push that data or marshal that data to the large core. Whereas it's much harder to predict which shared data you're going to touch, or which core is going to touch the shared data. You can imagine ways of doing that, but it's very tough. People have tried to build mechanisms. There's a body of literature that tries to predict which thread is going to touch the shared data next, and speculatively push that data to that thread core. And it turns out the accuracy of those mechanisms is not very high. Whereas the accuracy of data marshalling, you can tell me what it is. Now this is the pop quiz to see if you actually read the paper. You guys remember the accuracy of data marshalling? 60? Is it that low? Could be actually. I think coverage was high, accuracy was relatively low. Oh, nobody remembers? Okay. Well, you don't know which data statically, right? Data addresses are not available statically. And you have control flow that's changing dynamics, but it cannot be 100% accurate. Unless your control flow is always right, always the same. Okay, you can look at the paper again. Okay, we've covered these trade-offs. This is very similar to the trade-offs that we have in ACMP. You have fewer parallel threads versus accelerated critical sections, but you can amortize that. You have the overhead of critical section call and critical section dump versus the better lock locality. And this turns out to be better, a good trade-off if the critical section is contended, as I said earlier. And we get more cache misses for private data versus fewer misses for shared data, because we're keeping the shared data on the large core. This is a problem. In general, actually there's no general statement, but usually it makes sense. When I think of it, it makes sense to have more cache misses. What am I trying to say? Shared data that a thread touches, a critical section touches, is greater than the private data. That's not always the case, interestingly. But let me give you an example. Let's say you're inserting, this is your private data that you're inserting into a priority heap, and heap is a big heap. When you're, and this is a critical section, this insertion is a critical section because this heap is shared by many threads. If you're going to do this insertion, the only private data element is this new node that you're inserting. shared data elements that you touch is quite a bit, quite a few. So this is what I would normally think of when you have private data versus shared data. But it turns out in some cases you add a lot more shared data, private data into a small set of shared data that you touch. So this is a trade-off. And transmission is reduced if shared data is greater than private data. Shared data that's touched is greater than private data that's touched. And we will get back to this, or you can tell me what it is. So you've seen the performance results. I'll go over this quickly. The comparison points are symmetric multicore, asymmetric multicore, where you have conventional locking, but large core accelerated the serial part, and accelerated critical sections. And there are 12 critical section intensive workloads from different domains, simulated on a multi-core simulator. And these are the characteristics of the large core and small core as you read in the paper. The main difference is large core is auto border with a reasonable size instruction window and a longer, deeper pipeline. It's wider. Whereas small core is wimpy, just like Sun Niagara. So you can put many of those. And this is the on-chip interconnect. And if you look at the performance improvements, you can divide the benchmarks workloads into workloads with coarse grain locks, where the programmer did not put much effort into optimizing the critical sections. If the programmer doesn't put any effort, they could lock at the beginning of the program and at the end of the program, unlock at the end of the program, right, at the end of the thread. And everything is serialized. That's a coarse grain lock. If the programmer puts a lot of effort and the locks are fine grained, meaning they try to minimize the size of the critical sections, such that they're at most a few instructions if it's possible. May not be possible, right? Because it's also dependent on your data. But then the program can optimize the data. For example, if your shared data structure is a huge tree or huge priority, how does the programmer ensure that you get small critical sections when you're when some thread is updating that heap? Well, you can partition that heap such that different parts of the heap is protected by different locks. Okay. That way you can reduce the size of each critical section. But you can imagine how much programming effort that requires, especially in a data structure like a heap. Well, you can write that. Maybe that should be an assignment in this course. Writing a much more parallel heap than a single block. Well, an easy way of protecting that heap is whenever before a thread accesses that heap, you have a lock. And you update that thread updates that heap or reads that heap, and it unlocks it. But you could do it much more fine-grained. You could not block every node even. Of course, there's an overhead associated with that. But that is the finest grain you get, perhaps. Same as hash tables, right? Hash tables again. That's easier to parallelize. If you have a hash table, you can lock every bucket. Have a lock associated with every bucket. That's much easier to reason about also than a heap. So yeah, fine-grained locks, programmer optimized code. And if you look at this performance graph, when you have coarse-grained locks, the speed up that you get with accelerated critical sections is significant compared to both symmetric multicore and asymmetric multicore. This is called acceleration sequential kernels, but it's really accelerating the serial part of the program. That's ACM. And the performance benefit is significant. I'd like to emphasize that this is very important. This is actually very, very important. If you're doing your projects, the comparison points here for symmetric multicore, asymmetric multicore, and accelerated critical sections, first of all, they're all equal area systems with some definition of equal area. But the number of threads of a program on a given system is the number of threads that provides the best performance on that system. So for example, when we run puzzle application on the symmetric multicore system, maybe the best number of threads is 8. And here we have 32 small cores. And when we run it on ACMP system, the best number of threads is 9. And when we run it on ACS, maybe the best number of threads is 15. Those are the comparison points. The comparison point is not 15 for all. Because if you do 15 for all, what will happen? Any guesses? The baseline symmetric multi-core system is not performing the best at 15 threads, right? Because the application is not scalable to 15 threads in the symmetric multi-core system. So you really need to pick the best threads. This may not be easy to do actually in real life. In real life, how do you decide what's the best number of threads? Even that is dynamic, depending on the resource contention. If you're interested in that, you can read this paper. You need to do a project on that. Author Suleiman wrote another paper called Feedback-Driven Threading. The system dynamically decides the number of threads. Is this ASPLOS? Yeah, ASPLOS 2008. Dynamically decide the number of threads that you actually execute in a program, depending on what is your scalability bottleneck, right? But when you're doing the comparisons, you have to do the fair comparison. Because you could, another point you could compare it, you can assume that it's all 32 threads, right? All of the applications are 32. Every one of them has 32 threads, regardless of the system. Again, that's not a fair comparison, right? Why? Well, I guess I'll show you why. Because of this. Because if you look at an application, at 32 thread points, if you look here, for example, the performance gain that we get from accelerated critical sections looks huge, right? The baseline with 32 threads is its performance is here. The ACMP with 30 threads, its performance is here. And ACS with 30 threads is the performance is great. But nobody would execute this program with 32 threads on the baseline. Actually, at least nobody who's sane would do that. Because that's obviously you can execute this program with 16 threads and get much better performance than with 32 threads. So you're going to be careful when you're doing these parallel performance comparisons. Okay. So if you look at the fine-grained locks, the performance benefit of accelerated critical section is not very high because it's still high because there is some contention, and they're not as fine-grained. The locks are not as fine-grained as we would like them to be, perhaps. Maybe the programmer did not put enough effort, or maybe it was not easy. Well, they're the same thing. And the performance benefit is not as high. But overall, the performance benefit is about 40% compared to symmetric multi-core, and maybe around 30% compared to asymmetric multi-core. Okay? You've seen these results. And scalability of multiple benchmarks, 7 of the 12 workloads improved. What does that mean? Scalability improvement means that the number of threads at which performance saturates increases. So here, if you look at I'll take the same example, the online transaction processing workload. The green, the number of threads where the performance of the symmetric multi-core system saturates is, I don't know, can you guys see that? 16? Okay. You have good eyes. And the number of threads where the performance of the ACS system saturates is probably somewhere between 24 and 32. So that's scalability of that workload improved. You could add more threads and get better performance. Okay, so that's the summary. Critical sections reduce performance and limit scalability, and if you execute them in a powerful core, you can improve both performance and scalability. Now there are, of course, shortcomings of this work, and you've seen improvements on it with bottleneck identification and scheduling. I think I'll cover that, and then we'll end the lecture after that. But think about other ways of improving it. Right? Here, we may be shipping the critical section to the large core, but that may not be improving performance. And large core may not be the best way to improve the performance of that critical section. If this critical section is really important, maybe you design a core that's optimized for executing these critical sections. The question is, what would that look like? That could be an interesting research topic, right? Because this is the bottleneck of your program. That's what you want to accelerate. And maybe these bottlenecks have similar characteristics. And if you can design specialized cores to accelerate these bottlenecks, maybe you can get much better systems than what we have today. Large core is just one easy way of doing it because we do not know how to accelerate the bottlenecks otherwise. So if you want to generalize the idea, we would like to accelerate all the bottlenecks, not only critical sections. And that's the next step. Now you read the paper. This is a very brief summary of the paper. You already know that performance and scalability of multi-threaded applications are bottlenecked or limited by serializing bottlenecks. And there are different types of them. Critical sections, barriers, slow pipeline stages. And the importance of this bottleneck actually changes over time. You have different bottlenecks that become more important. As you read the paper, you know that. So the goal of this work is to dynamically identify the most important bottlenecks and accelerate them. There are two key questions, of course. How do you identify the most critical bottlenecks? And when you say critical bottleneck, I'd like to think of the bottleneck that is on the critical path of execution. Basically, if you accelerate it, you will definitely gain performance. And at some point in time, some code that's executing in a parallel application must be on the critical path of execution. In a single-threaded program, some instructions are on the critical path of execution. Some instructions may not be because you execute them out of order, and their latency may be hidden. Here you have multiple threads. Some threads are on the critical path, some threads may not be. So how do you identify these most critical bottlenecks, and how do you efficiently accelerate them? So the solution that you read is bottleneck identification and scheduling. Again, it's hardware, software cooperative. If you can do this purely in hardware, that's another research topic, and Intel would be very interested in you. Because this is a real problem they're facing. And if you can find a way of purely doing this, doing whatever is done purely in hardware, maybe you'll be like the next branch predictor person in the 90s. that would be the analogy. So software annotates the bottlenecks with bottleneck call and bottleneck return instructions, and implements waiting for bottlenecks with a special instruction, bottleneck wait. And hardware uses these special instructions and identifies the bottlenecks that cause the most thread waiting using this bottleneck wait instruction, and accelerates those bottlenecks on large cores of an asymmetric multi-core system. And it turns out this improves multi-threaded application performance and scalability beyond what accelerated critical sections can do. And performance improves with more cores also. So I've already shown you. The idea is to generalize these bottlenecks, right? Accelerated critical sections handles only this, but we want to generalize more. And if you can generalize more, that's another research direction. What else is missing here? Right? What are the other bottlenecks in a parallel application? For example, this doesn't include the resource contention bottlenecks. Right? That's an obvious next step. So one observation in this paper is limiting bottlenecks change over time. And I'll give you a cooked up example. And whenever you have these observations, it's always good to come up with cooked up examples. It doesn't matter if it's a cooked up example. Whatever you cook up, you should know that there's a programmer in the world who will cook up that for a real problem. Or cook up something like that. Because there's so much software out there, and there will be programmers that are writing some similar code. So this is a cooked up example where you have a start. Each thread does this. We start with a full linked list A, and we're going to copy elements from that linked list to an empty linked list B. And each thread takes one element and copies it to the next linked list. So there's a lock in which the thread traverses list A and removes an element from A, does some computation on that element, and locks the next list, list B, and inserts that element into that list. It's cooked up, right? But you can imagine programs potentially doing this. You're copying data in some way. Maybe you do some more operations to figure out what is X. Right? Maybe you don't move the entire linked list from one to the other. Okay, so this is a critical section, obviously, with multiple threads trying to access this linked list will contend for it. And this is another critical section. If you look at the execution of this program with 32 threads that are started in parallel, initially this linked list is full, and there's lots of contention on this linked list. The y-axis is contention in terms of number of threads that are waiting for this lock. And initially, there are many threads waiting for lock A, so lock A is the limiter. But soon after 10 million cycles or so, lock B starts becoming the limiter. Because this list starts becoming populated. And because you have a single large lock that protects the entire list, every thread that's trying to lock it will need to wait for the thread that's currently inserting into this. So this shows that limiting bottlenecks change over time. And there are some cases where it's not clear what is the bottleneck. Then what do you do in that case? We accelerate both if you want to improve performance. And this is an example. You've seen this in the paper from a real application, MySQL, with 16 threads that shows 2 locks or 2 critical sections in this real application. And it shows the contention on the critical sections and how many threads are waiting. And if you look at some portions of the code at a very fine grain, this is millions of cycles, and the maximum is 8 million. At a very fine grain, the bottlenecks change very quickly. It's the log line, this is the database log. That's the bottleneck here. That's making many threads contend. And in some other parts, it's the open lock, where you're opening the database tables that is making lots of threads contend. And this is dynamically changing very quickly. So you already know some of the previous work. HCMP accelerates MDAL bottlenecks, serial points, right? Accelerated critical sections accelerate only critical sections. But it also has another shortcoming that we briefly talked about. It doesn't take into account the importance of critical sections, as you mentioned. It just gets to a critical section and stupidly ships it to the large core. Simple. And at the time it was good, but now it sounds stupid after you're reading the bottleneck identification and scheduling paper. Right? This is like you finding CM5 paper. Not very smart. Now I look back on our previous work and find it not very smart. Right? And that's how it should be. That's how you improve in research. So it doesn't take into account the importance of critical sections. And there's another work that I would recommend you to read. This is the feedback method pipeline. Basically, how do you accelerate pipeline-based parallel program? Basically, what it does is it's a software-based library that figures out which pipeline stage, is it A, B, or C, has the lowest throughput, meaning is the slowest one that's making other stages wait. One way you could figure that out is how many A's are queued, right? That could be one way. Another way of figuring out that is there are queues between A, B, and C. So when you're communicating between A and B, there's a software queue. So when A executes, it pushes its result into the software queue where the next instance of B can pop the result. So if that queue gets full, you know that B is not going fast. And the software-based library can figure out which stage has the lowest throughput and shift that stage to a large core instead of executing it at a small core. That's one way of accelerating a pipeline-based parallel program. But the downside is, because it's software-based, it cannot adapt to these fine-grained changes. Okay. So no previous work can accelerate all these 3 types of bottlenecks or quickly adapts to fine-grained changes. And you know the general mechanism, hopefully. I don't think I'll be able to go into detail in the remaining time. But we want the general mechanism to identify the performance limiting bottlenecks and accelerate them on the large core. I guess I'll cover just this also. Key insight is, at least in this work, and I encourage you to improve on this insight because it's not flawless. There are better ways of doing this. The key insight is thread weighting reduces parallelism and is likely to reduce performance. If we can identify the code that's causing the most thread weighting, it's likely on the critical path. if you can dynamically identify bottlenecks that cause the most thread weighting, and if you can accelerate that, you would be accelerating critical path. That's the key idea. And we would like to do that. Question is, how do you do this? You already know this. Basically, the compiler, library, and the programmer annotates the bottleneck code and implements waiting for bottlenecks with special instructions and generates a binary containing these instructions. And the hardware measures how much waiting each bottleneck causes using these bottleneck wait instructions and accelerates the bottlenecks with the highest thread waiting cycles. And I think I'll go quickly into this. So how do you actually annotate the bottlenecks? This is a critical section. Right? Critical section is outlined into a function, and you get a bottleneck call that identifies the critical section, bottleneck ID, generic, and the target PC, this is the beginning of the critical section, and the critical section is delineated with the bottleneck return from the bottleneck ID. And this waiting for the critical section, if you cannot acquire the lock, if the lock is busy, somebody else has the lock, then this waiting that's normally implemented as software now is moved into hardware. The hardware has an instruction that takes a bottleneck ID and an address to watch. When that address changes, when somebody else finishes its critical section, it updates that watch address, and that address changes, this bottleneck now becomes available. Well, this instruction wakes up the thread that's waiting on that bottleneck. And this is used to keep track of thread waiting cycles. And these are used to enable acceleration because they delineate the bottleneck. And you can think of the same thing for barriers. I think I'll cover this and then we'll stop there. And then you already know. The paper doesn't describe this in detail. Did you guys understand it? Or you can do, you can identify bottlenecks with barriers. So this is a very common barrier code. A thread enters the barrier, and while not all threads are in the barrier, it just waits. Right? And then it exits the barrier and can continue with whatever it's doing. But this is really the code running for the barrier. Right? This is the parallel part. If you think of this is the barrier. You have some code running here, and that code is here. So you have a bottleneck call to that code, and at the end of that code, there's a bottleneck return that goes back, and the thread now enters the barrier. That's where the bottleneck is, and it starts waiting if there's at least one thread that's not at the barrier. That's where the bottleneck wait instruction comes in. When the thread starts waiting, you get a bottleneck wait instruction that's executed. Okay. And you can do this for pipeline stages as well. And this is what a pipeline stage looks like. Basically, you have this A part of the code that does the work and gets input from the previous stage. And how does it get input? It reads a queue. It dequeues some work. If the queue is empty, it cannot dequeue some work because nobody produced that work yet. And at the end, after doing the work, it's input. It outputs its result into an output queue, which somebody else, some other stage will read. And if it cannot output because the queue is full, it waits. It's stalled. And you can measure whether it's stalled because of an empty queue, or because of an empty input queue, or because of a full output queue, using these bottleneck instructions. And you can know which bottleneck is causing the wait. If the input queue is empty, then the previous stage, pipeline stage, is causing the problem, right? It's making this thread wait. If the output queue is full, then the next pipeline stage is causing the problem because it's not taking results quickly enough. That's how you increment the thread waiting cycles and associate them with a bottleneck that's actually causing waiting for a given thread. Okay, I think I gave you more detail than the paper did on this particular topic. But once you have this bottleneck wait instruction, the hardware can actually measure the thread waiting cycles when it executes that bottleneck wait instruction. And once it figures out which bottleneck has the highest waiting cycles. Basically, there's a table that associates bottleneck ID with number of waiting cycles. And if a bottleneck is causing lots of waiting cycles, it can get shifted to the logical. But I think let's stop here, because they're going to kick us out.